In this video, we'll explore the twin paradox using the special relativity flat spacetime of Minkowski diagrams and animated world lines. We'll begin with the classic idealized version, then move to a more realistic trajectory where the traveling twin accelerates smoothly. The goal is to build intuition for how proper time accumulates along different paths through spacetime. The twin paradox compares the aging of two twins, one who stays on Earth and one who travels at high speed and returns. When they reunite, the traveling twin has aged less. The key question is, why? A Minkowski diagram lets us see motion as geometry. Time runs vertically, space horizontally, and light rays always form 45-degree lines. World lines represent the histories of objects. Proper time is the time experienced by each twin. It depends on the path through spacetime. A steeper world line, meaning slower motion, accumulates more proper time. A shallower world line, faster motion, accumulates less. In the idealized version, the traveling twin moves at constant speed, instantly reverses direction, and returns. This creates two straight segments with a sharp kink at the turnaround. It's simple, but not physically realistic. This animation shows the idealized twin paradox. Notice the straight world lines and the sudden jump in simultaneity at the turnaround. On reunion, twin B is younger, since less proper time has elapsed for him. Even though the turnaround is unrealistic, the idealized model captures the essential physics. The traveling twin's world line is less vertical, so it accumulates less proper time. In reality, no rocket can flip direction instantly. Real trajectories involve smooth acceleration and deceleration, which means the world line should be curved, not kinked. To make the model more realistic, we use a smooth step acceleration profile. This gives a smooth increase in velocity, a coasting phase, and a smooth deceleration to rest at the turnaround. The inbound leg mirrors the outbound. With smooth acceleration, the world line becomes curved. When B speeds up, the world line tilts more horizontally. When B slows down, it becomes more vertical. Proper time accumulates faster when the world line is steeper. This animation shows the realistic trajectory. Notice how the world line curves smoothly, and how the proper time increment changes continuously as the velocity changes. Comparing this to the straight line trajectory, both for velocity of 0.8 times the speed of light, twin B ages more, here. Even with a realistic trajectory, the conclusion is the same. The traveling twin ages less. The curved world line still spends more time tilted away from vertical, meaning less proper time accumulates. The twin paradox is not caused by acceleration itself. It's caused by the geometry of the path through spacetime. Acceleration simply changes the path. We've seen how Minkowski geometry explains the twin paradox. Whether we use a simple toy model or a realistic trajectory, the traveling twin's world line is shorter in proper time. This appendix shows the relevant equations from Einstein's special theory of relativity. In special relativity, the spacetime interval is the fundamental geometric quantity. It combines time and space into a single invariant expression. For motion in one spatial dimension, the interval is ds squared equals dt squared minus dx squared. All observers agree on this value, even if they disagree on the individual values of time and space. Proper time is the time measured by a clock moving along a world line. It's given by the square root of the spacetime interval. If we express the motion in terms of velocity, the formula becomes d tau equals dt times the square root of 1 minus v squared. This shows directly that faster motion reduces the rate at which proper time accumulates. The Lorentz factor, gamma, tells us how much time dilation occurs at a given velocity. As the speed increases, gamma increases, and the moving clock ticks more slowly relative to an inertial observer. This is the mathematical heart of the twin paradox. The total proper time experienced by a traveler is the integral of the proper time increment along the entire journey. This means the aging difference depends on the full velocity profile, not just the endpoints. Two travelers who start and end together can age differently if their world lines differ. In Minkowski geometry, a straight world line represents constant velocity, while a curved world line represents acceleration. Curved paths are shorter in proper time than straight ones connecting the same endpoints. This is why the traveling twin ages less, regardless of the details of the acceleration. To model a realistic spacecraft trajectory, we use a smooth step velocity profile. This function increases smoothly from 0 to the cruise speed, with zero acceleration at the endpoints. It produces a curved world line that reflects realistic motion without the mathematical complexity of full relativistic rocket equations. In the smooth step model, the velocity changes continuously, so the proper time increment also changes continuously. During high-speed coasting, the world line is shallow and proper time accumulates slowly. During acceleration and deceleration, the world line steepens and proper time accumulates more quickly. It's important to emphasize that acceleration does not directly cause the aging difference. Instead, acceleration changes the shape of the world line. The geometry of that world line determines how much proper time accumulates. The twin paradox is fundamentally a geometric effect. These are the core equations behind the twin paradox. They describe how motion through space-time determines the passage of proper time. Whether the world line is straight or curved, the mathematics is the same, and the geometry tells the story.